Welcome to the presentation on unsupervised learning of metric representations with slow feature analysis and omnidirectional views. My name is Mathias Franzius. I work at Honda Research Institute Europe. My co-authors are Benjamin Metka, Mohammed Harris, and Ute Bauer-Wersing. The target of this work is unsupervised self-localization with low computational cost and low-cost sensors. Our setting is a wheeled service robot self-localizing in limited space, like a garden, using an up-facing fisheye camera or catadioptric system. We contribute an algorithm for unsupervised learning of a globally consistent metric 2D robot position using uncalibrated omnidirectional images without a GPU or large CPU and without labeled position data. When we want to estimate the robot position from a single input image, the naive approach would be to do a regression from each input image to the positions as measured by odometry. However, it's well known that odometry accumulates errors, so it drifts over time. That has an especially large impact for errors in estimated orientation. However, odometry distance estimates between any 2 points are more robust, especially for linear segments where no acceleration takes place. On the right you see some example. We did the ground truth trajectory on the left part, and on the right the estimated naive wheel odometry. Anyhow, it's worth noting that the short-term odometry is usually very good. Our approach has 3 phases, 2 training phases and 1 application phase. During the first training phase, the robot drives around in the environment and collects data. We assume that the trajectory contains straight line segments and that sufficiently often these line segments intersect each other. But please note that in contrast to SLAM loop closures, we do not need to identify these explicitly. Preferably, we learn slow feature analysis on the visual inputs. I will explain that in the next slide. We store the outputs of the SFA and the odometry for phase 2. This movement behavior is, for example, compatible with that of a lawnmower robot. In the second training phase, we perform unsupervised regression from the sensory representation to a metric 2D position. The core idea here is that we can use an additional geometric constraint of moving along a straight line with known distance between points on a line. Then, finally, in the application phase, we are able to compute the metric robot position from individual images, and optionally we can also integrate the odometry with Kalman filter to further improve the accuracy. Slow feature analysis is an unsupervised learning algorithm for the extraction of slowly varying features from quickly varying inputs like videos. If you're interested in more details, there is a nice introduction on Scholarpedia linked in the top right. The core idea of the algorithm is that temporal proximity during learning the phase leads to similar representations in the output. Mathematically, we minimize the average squared temporal derivative of each output while keeping certain constraints of zero mean, unit variance, and decorrelation of the outputs. It's important to note that we do use the temporal statistics of the input and the temporal derivatives during training, but once we finish training, we get an instantaneous input-output function. That means for one input image, we get one output. So you can't solve this by a simple low-pass filtering, for example. The algorithm efficiently finds the optimal solution by solving a generalized eigenvalue problem. And our application here is to find sensory representations of the robot position, which are low-dimensional, spatially smooth, and yaw orientation invariant, but not metric. You see 2 examples on the right. Y1 encodes the robot position in the north-south direction and Y2 in the orthogonal east-west direction. Under ideal conditions, the SFA representations may already encode the robot position in 2D very nicely, but practically it will also contain other environmental information, and this representation is certainly not metric. Now, if we could do supervised regression with known ground truth positions, we could solve this easily, but we have to do something different without knowing ground truth positions. So given the slow feature vector S computed from an input image at the position of the robot P, we want to find the weight matrix W such that the error epsilon is minimal for the estimation of P from W and S. For points along a line L, we can express each point P by using the line parameters alpha for its orientation and O for its offset, and the measured distance D from odometry. So for correctly estimated parameters alpha, O, and W, each point along a line can be expressed by the right-hand side here, W transpose times S, and also as being on a line as shown on the left, so this difference should be minimal. If we integrate that, if we sum it up over all points along each line, over all lines, we end up with a cost function that we can minimize in order to estimate these parameters W, alpha, and O simultaneously by gradient descent on C using the partial derivatives given here. We start with a simulator experiment in perfectly controlled conditions using Blender for visual input. We simulate an omnidirectional camera and use a rather arbitrary projection to panoramic views. Instead of using a single SFA step, we use hierarchical SFA because these inputs are high-dimensional. The architecture is not unlike a CNN, but since it's an unsupervised approach, we do not need labeled data and there is no backpropagation, and it's much faster. On the top right, you see the results for the training data using a supervised regression as a baseline and the unsupervised approach on the right. You can see that the lines along which the simulated robot moved are well represented. On the bottom there is independent test data. Both approaches very well represent the movement trajectory, and they have a similar average error of 39, respectively 36 centimeters. Next, we show results with an actual robot and an omnidirectional fisheye camera tilted upwards. And we can show that with the same approach as in the previous slide, we get also very good results for the supervised baseline and the unsupervised approach. The supervised approach has an average error of 12 centimeters and the unsupervised approach an average error of 17 centimeters. We have shown a system for the unsupervised learning of 2D robot position from noisy odometry and using an uncalibrated omnidirectional camera. The performance is similar to supervised regression, but it does not need any labeled training data. Also, the approach is much simpler than most SLAM systems. In the paper we show two more extensions. First, we can integrate the measured rotations between any two line segments, which improves the convergence speed and also reduces the risk of certain degenerate solutions. Second, now we have shown that each image yields one independent position estimate. Thus we can gain a further 20% accuracy by integrating these estimates with odometry using a Kalman filter. Thank you for watching.